Hi, this is Yingda from Alibaba. Today I'm going to talk about our work on Fangorn. It's an adaptive execution framework for heterogeneous workloads on shared clusters. This is a joint work with all my colleagues here at Alibaba Group. Modern distributed clusters are overwhelmed with more compute. Each day, there are more jobs to run, more data to process, and the scales and complexities of the workloads continue to grow. The resource efficiency is becoming extremely critical. Meanwhile, workloads are becoming more diversified, covering a wide range of scales, SLAs, compute patterns, and resource types. Take one day's data in Alibaba, for example. Every day, our computation platforms host over 20 million jobs, processing over 2 exabytes of data, with job scales ranging from 1 to over 500,000. And they come from multiple compute engines running various workloads. There are two main categories of architectures for big data systems. One is developed from the MPP system that is keen on latency, but it may face challenges as the system scales out. The other is developed from the BSP systems that scales well and obtains good throughput and stability. The two types of systems are also learning from each other today. As the core execution framework at Alibaba, Fangorn is designed to host a wide range of workloads that typically executed on both systems. In this figure, we show Fangorn's overall architecture. A distributed job can be managed by a standalone job manager or through Fangorn Job Service that includes an admin which manages a pre-launch, long-running containers pool. And there are several multi-graph managers that is responsible for managing concurrently running jobs. The service is capable of scaling up or down with cluster traffic. These multiple components work together to provide support for a wide range of workloads and on multiple types of clusters that include Yang, Kubernetes, and Fuxi, which is a proprietary cluster manager developed here at Alibaba. Fangorn adopts a new graph model to unify various workloads into one framework. Essentially, a graph represents a distributed job, and a stage is the logical vertex of the graph that can be materialized into multiple tasks. Its physical properties may include parallelism and resource type. Edges connect stages, and on Fangorn, an edge is not necessarily bound to data flow. Instead, it's annotated with different physical properties. In this figure, we show how a two-stage logical graph can be materialized into batch MapReduce, interactive MapReduce, or primary server just by different combinations of physical edge properties. It should be noted that both physical and logical properties of the graph entities on Fangorn can be mutable during executions. It allows the framework to provide the necessary adaptiveness during runtime. We know that pre-compose the optimal execution plan can be very hard, which is especially true for deeper graphs. To compensate, Fangorn as an execution framework offers the ability to reconfigure graphs that adapt to statistics collected during runtime. Here we show a few cases enabled on Fangorn that mitigates data skew with dynamic physical plan adjustments. The first is the adaptive shuffle that detects skew and automatically rearranges skew partitions, so that each downstream task is assigned a fair amount of data. For adaptive joint skew mitigation, not only data assignment and stage parallelisms are adjusted, the shuffle pattern is also reconfigured to be a mixture of full shuffle and broadcast shuffle that ensure pairwise join to be correctly and evenly performed across multiple join tasks. Other than the physical properties, the need to adjust logical properties is also quite common. Without sufficient statistics, optimizer may not be able to decide on the optimal plan. In this case, Fangorn allows optimizer to submit a plan with conditional options, and it will only finalize the decision when necessary statistics become available. Here we show an example of conditional join, where optimal join algorithm depends on the cardinality of intermediate data, and it cannot be predetermined. A conditional plan is submitted in this case. An optimal join type is only chosen by Fangorn after cardinality has been determined. It will then cancel the subgraph associated with the unchosen plan. Such decisions can be nested within multiple conditions. The ability to make runtime plan modifications allows more aggressive optimization to be performed, and it is a general capability that has found applications in multiple workloads. With Fangorn's graph modeling, an execution graph may contain different resource types different data transfer mechanisms, and different granularities of scheduling decisions. It allows various execution modes to be unified. For example, when each stage is scheduled sequentially and data is persisted between stages, we have classical BSP system, while again scheduling entire graph and pipelining data throughout give us an MPP-like system. More importantly, this facilitates hybrid solutions that allows different subgraphs to leverage different scheduling strategies to explore flexible trade-offs between latency and resource usage. With such mixture, hybrid execution can adapt to workloads of different sizes and characteristics, and Fangorn work together with optimizer to derive graph segmentation algorithms by incorporating various factors. One example of hybrid execution is shown here that considers both stage parallelism and existence of data barrier when doing the graph segmentations. Now we turn our attention to how deep learning are managed on Fangorn. Notably, there are several distinct challenges in hosting distributed DL. First, although it has been attained in many systems, distributed DL really do not fit into the paradigm that designed after the legacy MapReduce. Additionally, different types of DL workloads do not fit into one paradigm either. There are differences between PS and ring or reduce, and there are differences between training and inference jobs as well. Finally, we call computation logic carried out by user script. They are inherently harder for the execution framework to reason about. Fangorn's graph model provides the necessary flexibility to accurately describe different DL workloads. The adaptive framework also allows plan to be dynamically adjusted in a coherent way, together with DL parameter adjustment and coordinated checkpointing. Now we evaluate the performance and resource consumption jointly on TPCx against different execution modes. Game scheduling achieved the best performance but at a significant resource premium. In comparison, batch execution completes the benchmark with this resource consumption. Hybrid execution, on the other hand, is able to attain different trade-offs in between. With the resource-aware subgraph segmentations, noticeable performance gain is achieved with marginal resource overhead when comparing to batch mode. To understand the difference, let's look at the breakdowns of the execution timelines. We can see that while pipelining expedites execution, it requires co-scheduling of upstream and downstream stages, which, when done unwisely, can result in significant resource overhead. The process launching overhead of both your manager and each individual task can also add up, which is the price to pay for on-demand resource requests. With Fangorn now fully deployed at Alibaba, over 2.5 million jobs leverage hybrid execution per day, upgrading from the conventional batch execution. We have seen significant performance gain without additional resource costs. The production statistics also show that the subgraphs need not be huge, and then multiple subgraphs in the jobs are not so uncommon. Finally, we take a look at performance evaluated against TPCx-BB. As a newer benchmark suite, TPCx-BB evaluates comprehensively the performance of modern big data systems. It covers structured and unstructured data processing with relational and machine learning workloads. Our system is able to rank on top in both 30 and 100 terabyte categories. We refer to the official TPC reports for details. Here we would like to show by an example just how the adaptive capability of Fangorn helps to achieve this superior result. As it turns out, the join operator in Q19 can be significantly skewed, which, if unhandled, leads to prolonged job execution. With adaptive join, the skew partition is automatically detected and spread out to multiple join tasks. It results in a more efficient resource usage and much shorter execution latency. In conclusion, the heterogeneity of workloads can manifest in terms of scales, compute patterns, and resource types. And here we present Fangorn as the execution framework that is built on a new graph model and hybrid system architecture, which allows it to adapt to various workloads. Fangorn can dynamically reconfigure physical and logical properties, and its ability to combine multiple execution patterns within one single job will open new doors to explore finer-grained execution optimization for workloads of all scales. Today, Fangorn is fully deployed across Alibaba and on Alibaba Cloud, managing over 20 million jobs per day. With that, we would like to conclude our talk today, and please feel free to reach out to the email listed below if you have any questions.